So that would be this one. So I'll go back to my question. So all forms of expressing rates of reaction, we have 5 already. So this one is these are the first 3. The first one is based on unit volume of reacting fluid. This one is mass of solid. This one is surface area of solids, depending on the system. The other one is based on the volume of the reactor and the volume of the solid for gas-solid systems. My question a while ago was all these rates were all multiplied based on the basis for expressing the rates themselves, and they were all equated. They are all equal because these products of this represent the what? It represents
Moles, miss.
the rate. It represents the rate of change of the number of moles of I, or that would be, they all represent d and I dt. So if you're going to multiply all these r's with the basis that was used in expressing the rate of reaction, they all represent the rate of change of the moles of I with respect to time. Now, do you have any question in this particular part? Because this is very important in terms of expressing the reaction rate. So it is the problem, as I said, that dictates on what particular or in how will you express the rate of reaction. But majority of our problems are liquid phase, so it would be this one. So most of I per unit volume of fluid per unit time. In other reactions, it would be this, depending on what the problem requires. So do you have any question in particular to this particular section in our slide?
Miss. Hello, Miss Joshua, miss.
Yes.
Miss, may question ka, miss. Bali given, naging sila ng formula, miss. Bali, amo na gani sila, miss.
Amo na gini sila. Oo. But, Josh,
Okay.
this Ri, this R sub I prime, this R sub I double prime are representations only that were used by the textbook. You can simply represent it at this one, this R sub I prime by Ri, R sub I only, as long as you have defined the units after you have written the reaction rate. So it doesn't have to be with the prime or with the double prime, because anyway, anybody, if it's requiring you for the answer, would still look into the units of your final answer. This is the primes that were written here were simply used by the author to, shall I say, distinguish one rate representation from the others. But iyan representation. This could also be changed. Pero sa aton, Joshua, as I said, I'd like to emphasize, since our reactions are mostly homogeneous liquid phase reactions, if not liquid phase reaction, gas phase reactions, and it's still homogeneous, we're using the first one. These are only taught by Levenspiel. These were presented. That way, you will not always at all times limit only your understanding of reaction rate as the common set of units having moles per unit volume per unit time, because it could also have this other set of units. Now, this is again a rate equation because you have the presence of the derivative. If you don't have this derivative written, you only have the R and the K and the C here on the other side, just like the way it's written in FICEM, in the last part of your FICEM, that's a rate law. We will define the rate law later. So you would be able to distinguish the rate equation from the rate law. Okay? Any question? None? Okay. Now, the reaction rate is the rate at which a species loses its chemical identity per unit volume. Let me specify this one. This statement is true if the species that we're talking about is a reactant. So it loses its identity because it has to give way to the identity of the products that it will be producing. So this is in the case of the raw material or the reactants. They lose their identity. That's the rate in which they lose their identity. So moles of I per unit volume per unit time. The rate of reaction can be expressed as the rate of disappearance of the reactant or the rate of appearance of a product. So if the rate equation or the rate law that we are writing is expressed in terms of the reactant, I'd like to emphasize this, and I'd like to go back to the previous slide. If it's a reactant, all this would be negative because the reactant decreases in value over time. And since we want it in terms of just a quantity, how much does this particular reactant decreases its value per unit time, per unit volume of the reaction mixture, we write a negative sign in here before the R's. Again, that's for reactants. If when we talk of the products, then it's positive because the products of course, are being formed. As the reaction proceeds, the value of the most of the product with respect to the volume per unit time increases over time. So then it would be positive. In here, these are all, I think, based on the premise that we are expressing the reaction rate or the rate of formation of a product. But specifically, generally, when we speak of reaction rate, it has something to do with the manner in which the reactants react with one another. So it has to be negative. So whenever you see a negative sign here, meaning it's the representation of the rate of reaction of a reactant. So this is what it meant here. If it's the rate of disappearance, you have a negative sign for the R. If it's the rate of appearance, that would be positive. You have this example. If B is being created at a rate of 0.2 moles per decimeter cube per second, that is the rate of formation of B, since we're talking of B is positive, 0.2 mole per decimeter cube per second. Now, then A is disappearing at the same rate because you see there's a 1-to-1 relationship between A and B in our chemical reaction or in our stoichiometry. In terms of stoichiometry, 1:1. You will be taught on how this one is. So in the same way, we can say that rate is disappearing, or A rather is disappearing in the same rate. So negative. So you can see it's negative R sub A being equal to 0.2 mole per decimeter cube per second. The same rates, but this one is formation, this one is disappearance. The same value because in terms of stoichiometry, it's just 1:1. Now, and the rate of formation of A, now, take note, the rate of formation of A. So you may wonder, how can A be formed when it's actually being consumed so that B is produced? Look at it. Then the rate of formation of A is now negative. Why is the rate of formation of A negative? Because A in the first place is a reactant, so it cannot be formed. So it's negative 0.2 mole per decimeter cube per second. Notice also that since it's the rate of formation, the R here, as I have said a while ago, is positive. Because if it's being formed, the rate here expression is positive. If it's being consumed or if it disappears, it's negative. So now you have R sub A being equal to negative 0.2 mole per decimeter cube per second. I think conversely, we can say that the rate of disappearance of B, so that would be negative R sub B, is equal to negative 0.2 mole per decimeter cube per second. Why negative? Because B is not disappearing. It's being formed. And we are asking for the rate of disappearance of a product. So you place a negative sign here, and this would also be negative. This one here, okay, so that's my alarm. So this one here is negative since A is really disappearing, so this is positive. But if it's to be expressed in terms of formation, you see that this one will be positive and this one will be negative. Okay? Now, I have sample problems here, and I think these are sample problems in the book, but I'd like to discuss this with you. And this is the last part of the slide. So I'd like to discuss this at 1:30. So we'll have a 5-minute breather before we continue with these two sample problems. Use the second link that I have provided in our GC. So I will stop sharing for now. And let's see each other again using the second link that I have provided.